Again, when I ask you to use geometry, I'm asking you to draw out a rectangle, and I'm only going to ask you to do this rectangle stuff when it's possible, because there are problems that are very difficult to come up with the equation. So we have 1 plus 3 plus 5. And I'm trying my best, because I've never actually taught this equation this way, so that you can see, one, the next tower is a length of 3, the next tower is a length of 5. I'll even do one more. The next tower is a length of 7. But this side length that we're coming up with is like, this is n equals 1, this is n equals 2, n equals 3, this is n equals 4. So each one of these is a width of n, and that changes depending on how many towers you create. Now, this also gives a little clue away for you that the top of the tower is represented by this last piece, this 2n minus 1. So because I went to a width of 4, the height of this is 7, because 2 times 4 is 8, minus 1 is 7. But what we also need to do is create the same tower and flip it around, so then it will fit perfectly, so I have the same tower on here twice. Hopefully you can see that it's the same tower, just flipped upside down, so it's the same exact height. So when you think of the area of a rectangle, you can say, okay, well, a rectangle's base times height, except we only care for the half, that is the green half. All right, I'm tired of doing that, so I'm going to cut this in half. So our length of our base is n. Hopefully I've done a good job explaining this. But the height is this 2n minus 1, but then you have to add this 1 on top of it. So think of it as 2n minus 1 plus 1. And I think you can tell that these 1's will cancel. The half and the 2 will cancel. So the sum of odd integers, which is what's happening here, is actually equal to square numbers, n squared. And if you didn't know that, we have the equation right here. And now what I want you to do is prove that that's true. And that's using mathematical induction. And what we always start with is the base case. Now, I said in the first video that we start with n equals 1. We actually can start with any integer that it's stated in the problem. So in this case, it tells us to start at n equals 1. I think there's a problem in the homework, so change colors. I think in the homework, your base case says n is 4. So be ready for that. It's not always true that the equation works for n equals 1. You might have a stipulation over here or a condition that says that we start with n equals 4. So that will change your base case. So you have two options. One option is you can just look at the first number, n equals 1. Sometimes what I do is I look at this part and I plug 1 in for n. So that's what I'm going to do, just because I want to show you my thought process. So 2 times 1 is 2, minus 1 is 1. And that further confirms that this number was supposed to start off at 1. And then what I do is I go over to the second equation, this piece, and I plug 1 in for n. 1 squared is 1. So then I just have this kind of lame statement, since 1, what we got right here, maybe I'll even highlight it, that 1 equals that 1. Oops, accidentally highlighted something up there. The base case is true. So what we're doing is we're setting up that first domino. So we know that this equation works for the very first situation. So now what we have to do is the inductive step. Switch colors again. And what the inductive step is that we have to prove that it works for the next term on any situation. N equals k plus 1. I don't think I write this anywhere else, but it's the next term. Just like when we did the recursive definition in the earlier units, we're doing the next term. So what I'll do is I'll rewrite everything as it looks. 1 plus 3 plus 5 plus 7. And I change this n to be k. But I need the next term as well. So the next term is taking that n and replacing it with k plus 1. And I know this is not easy, so I'm, please write down any question you have. But right now I don't know what your question is, so to me this makes perfect sense. And what we want to show that this equation works for the next term. Now remember, it's no longer n that's squared. The next term is k plus 1 squared. So by setting up the dominoes this way, we already proved by the base case that this equation works, for n equals 1, that's the base case. And because I wrote it in terms of k, it equals k squared, not n squared. So this is equal to k squared. And don't forget about this piece now. And I hope you're okay that I'm going to distribute that in there. 2k plus 2 minus 1. Well, I could even simplify that further. That's k squared plus 2k plus 1. And look at that. This is a factorable problem. What are factors of 1 that add to be 2? Well, I could write k plus 1, or I could just write k plus 1 squared. And that's exactly what I wanted to show. So what the inductive step is doing is taking the first domino, knocking it over, and proving that the equation still works for the next domino. I know this is confusing stuff, but we're done with the proof. And even if this is confusing, I think you guys can do the algebra to show this step. Or you could, and this is my box that says I'm done, or you could say that the inductive step is true. Just double checking I'm done on this page. So here's just another one where they give you the formula, so you don't have to come up with the formula yourself. But you're practicing mathematical induction. So start with your base case. And you can just start with, I'm pretty clear that the first number is 1. But again, I like to show the step that I'm doing n equals 1. So I'm plugging 1 in for n here. Well, what's 1 squared? It's 1. And then I go to the right side. And I say, okay, well, what's 1 times 1 plus 1 is 2, times 2 times 1 is 2 plus 1 is 3, all over 6. Well, that's saying that 1 times 2 times 3 is 6, divided by 6 is 1. Oh, good, I got what I needed. 1 equals 1, so I set up the first domino. And sometimes I just have this blanket statement. Since 1 equals 1, the base case is true. By the way, you might have math professors in college that make you write out full sentences. I think you'll look back and you'll say, Mr. Higbee took it easy on us. And maybe they'll, I don't know, maybe they will be even worse. Or maybe they'll be easier than me, I don't know. But the inductive step is just saying n equals k plus 1. So again, the way I like to do this is my next domino. And I realize now I don't have much space to show you this step, is I just write out what we know is already true. Plus dot, 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 plus, again, I'd like to rewrite this one. And then I need to rewrite that next term. And as a quick reminder, I just write down what I want to show. I need to continue to work until I get all of these n's to be k plus 1s. And I've actually seen students, and I'm okay with this, your math professor in college might not, is I've seen students do scratch work at the top of their page where they figure out what all of this simplifies to first. n being k plus 1 can't simplify, but this n being k plus 1 plus this 1 would simplify to be k plus 2. And then this n switching to k plus 1, I've seen students that will actually distribute that. So they then write 2k plus 2 plus 1, so they know it's plus 3, and it's still all over 6. I don't like how I wrote that. Don't really like how I wrote that either. But that's how I know that I'm done with this process. So all I know so far is the first domino was correct, that this first equation worked. And because I wrote it with k, I need to rewrite it with k instead of n. Now remember, these are just variables. Like, who really cares if they're k's or n's? Well, how about this? Let's get the same denominator on this, because I didn't give myself much room. So I need to multiply the top by 6 as well, and maybe you FOIL that out. We're talking about k squared plus 2k plus 1. And then from there, and maybe I should have FOILed here as well. And again, I do realize I didn't give you much space. 2k squared plus 2k plus 3k. Sorry, 2k plus 1k is 3k plus 1. This will be all over 6 when I combine those same denominators. 6k squared plus 12k plus 6. And again, I need to distribute some more, so I'm looking at 2k cubed. Let's see, this would be 3k squared plus that 6k squared is 9k squared. Let's see, k plus 12k would be 13k plus 6 all over 6. And here's kind of a shortcut for you. And it's been a while since we've done this, but if I'm doing this correctly, this needs to simplify to what I want to show. So I've seen a few people do this differently. I kind of have the preference of factoring the way we did it early in the year. Remember when we did synthetic division? -1 in that little box. 2, 9, 13, 6. And break it down this way. So 2, -2, adding straight down, adding straight down, adding straight down. So k plus 1 is a factor of that. And then remember, we could just continue straight down and do -2 as well. So straight down 2, -4, adding straight down, -6, adding straight down. And what you notice is you're left with 2k plus 3, the last factor. And for the sake of simplicity, I know a couple things. I know I didn't give you enough room, and I know it probably seems like magic, but I'll let you go ahead and just jump to what you want to show at this point, as long as you show that work. And because we showed all of this work and what we want to show, you can put that box and say, hey, I'm done with this proof. And I held off on saying that you were doing a proof because I didn't want you guys to be super scared at the get-go. But that's what this is. Mathematical induction is a proof. So I think I'm going to stop at this point because I have several more problems to do, but I might work a little bit quicker through things. And I think I might skip this one. I think the formulas that I'm coming up with are a little bit more difficult than I want you to know for the upcoming test. So be ready for that in your assignment. I might skip a problem on there. And I'll see you in the next video.